I want to show you a demonstration and then take maybe like 3 vocabulary words, and that's about it for today.
Okay.
So in the background, my oven is turned on to 500 degrees, and I have a few things in there I want to show you. Let me go and open it up. So this has been baking for about 10 minutes. It's foil at 500 degrees, but I can hold it because there's not much mass to this foil. So even though it's at that temperature, it's not burning me because the amount of atoms in this foil is so small, it can't transfer much heat energy to my skin. It doesn't hurt. It's the same reason why the light bulbs in your house, if they're fluorescent lights, the gas in there is about 10,000 degrees. But you can touch the light bulbs and they feel cool to you. It's for the same reason. The amount of atoms in there is so small, they're at 10,000 degrees Fahrenheit, but the energy that they transfer is not very much. It's not enough to hurt you. So just to show that my oven is at a very high temperature, I have in here a steel ball too. I want to show you and get that out. I'll try this at home. Okay, so let me turn the screen down so you can see this. So this is just some ice. And I have in here a steel ball. If I can get it out of here with the tongs. It's at 500 degrees. There we go. So you can see that the oven is quite hot and the steel is at the same temperature as the foil was at, but I could hold the foil in my hands and my hands feel fine. But the steel ball is a totally different story. And that's because of the amount of mass in that steel ball. So I squish up the foil to make the atoms more compact, put it back in the oven and see if that makes any difference in the outcome. So I'll let it cook for a little bit and come back to it and see if that makes any difference in what the foil does. And while that's doing that, I'm going to give you a couple of notes to write down. And we'll come back to the foil after that. So the main thing to know today is thermal energy. And this is the reason why the steel ball went right through the ice while the foil didn't hurt my skin. So thermal energy is defined as total energy of the molecules. And it depends upon 2 things. It depends on the temperature and the number of molecules. So higher temperature, higher amount of molecules, which means more mass, means more energy. And because the steel ball weighed a lot more than the foil did, it had more thermal energy to give to the ice, and the ice melted because of that.
So the energy is like the heat, I guess?
Exactly. Yeah, very good. Exactly. Yeah, so heat would be a word for thermal energy. It's the transfer of thermal energy. That's right. Did we define temperature yesterday? I know we talked about it being the motion of atoms, but did we give you a definition of temperature? Well, just in case, if you don't have.
Yesterday.
Sorry?
I wasn't there yesterday, so I have no idea.
Oh yeah, I guess none of you were here yesterday. Well, Carl, I think you were here, I think, Carl, but I don't think.
Yeah, so I've got temperature is the average kinetic energy.
Okay, so you got that down. Okay, so
Yeah.
I'll write it down again for those who weren't here yesterday. So it's the average kinetic energy per molecule, which basically means how fast the molecules are going. So higher temperature means faster motion of atoms. And yesterday when I showed you all, I put dyes in different temperatures of water. I had boiling water, room temperature water, and cold water. And I put a little bit of dye in each one. And you can see that with the highest temperature, the dye dispersed very quickly. Well, with the cold temperature, the dye didn't really move much at all. And that's due to the motion of the atoms. Let me go ahead and check on the foil and try it while you're writing down these notes. Okay, it should be hot enough. Let's see. Okay, so I'm gonna just put the foil in the ice. Can you hear it sizzling? I don't know if you can.
I can't.
No. Well, it's hard to see on here, but it definitely melted the ice on here. I know it's not the clearest video, but it was sizzling and melting the ice. So it was the same mass of foil. The difference is that it was not spread out. So with it being spread out, I could safely hold it in my hand because the atoms were just so far apart from each other. But in here, with it being crunched up, the temperature is the same in both cases, whether it was spread out or crunched up in a ball. It's still 500 degrees. But the difference is how compact it is. With more atoms in a small area, more energy was transferred from the foil to the ice, and that's why it melted the ice. Well, with the foil being spread out, it wouldn't have done anything because it felt cool to my hand. So the energy was present, but it was dispersed. Let me get this out of the way.
Wait, so since light bulbs aren't that big, how come the energy, like there's not a lot of energy there?
Well, that's a good question. Well, it has to do with the gas itself. So the light bulb itself is quite big, but the amount of gas inside the bulb is what's the important thing. And there's not much gas at all inside the light bulb. It's almost a vacuum. And so because there's very few atoms inside the light bulb, that's why it can't transfer energy very well and why it feels cool to you. Okay, let's go ahead and end here for today. And I did assign on GradeLink a few questions, but we'll skip those today and go back to those tomorrow. So there'll be no homework today.
Thank you.
You're welcome.
Okay, thank you.